Welcome to the lecture series on digital electronics. In today's lecture, we are going to explain how a 2's complement parallel adder cum subtractor circuit works. So, previously we have seen the working of a 4-bit parallel adder which uses full adders. And we have seen that by using that circuit, we'll be able to perform addition of two data each containing 4 bits. And in today's lecture, we'll be looking at how to convert with a little modification the same circuit to both perform both addition and subtraction of the data of 4 bits. So, and that is called as that combination logic circuit. We'll be calling it as 2's complement parallel adder cum subtractor circuit. And in this lecture, look at the circuit, and before looking at that circuit, we'll try to find out, uh, learn the concepts that make possible as to perform the two different operations by using one circuit. So normally we can see that how a subtraction is performed. The subtraction of a minus b, for example, a is the data of 4 bits and b is the data of 4 bits. And if you see that the subtraction of a minus b, you can see that can be done by taking the 2's complement of b and adding it to a. That means the subtraction is converted. The subtraction operation can be looked as addition operation when we take the 2's complement of the subtrahend and add it to the minus end. That is, if you take the 2's complement of b, then the 2's complement of b is actually minus b, and if you add that to a, though we are performing the addition of 2's complement of b with a, the operation is equivalent to subtracting b from a, or it is equal to subtraction a minus b. And this is what we do with the combination circuit and what we want to achieve with the combination logic circuit. And you can see that how you take the 2's complement of b. So there are many ways to obtain the 2's complement of b. So here we'll be obtaining the 2's complement of b by taking the 1's complement first and adding 1 to the least significant pair of bits. That is, first obtain 1's complement of the given data, and after obtaining 1's complement you add 1 to it. Then the result will be the 2's complement of the required data. Then, but so all this is okay from theoretical point of view, that is with paper and pen. But how to obtain these complements? By using the hardware, that is by using logic gates. and you can see that we already know that we have an inverter, that is NOT gate, and the output of NOT gate is the complement of its input. The output of NOT gate or inverter is the one's complement of its input. So I can say that for 2's complement, we have to first obtain 1's complement and then add to 1 to the least significant pair of bits. So to implement that 1's complement, we use inverters or the NOT gates. So for each bit of the data, or for each bit, or to obtain the 1's complement of each bit, you need one inverter, right? So for example, if a data contains 4 bits, then we require 4 inverters to complement each bit, or to obtain the 1's complement of each bit, or the 1's complement of the 4-bit data. You require 4 NOT gates, one for each bit. In this way we can obtain the 1's complement of the given data. Then how to obtain the 2's complement? So after obtaining 1's complement, we know that if we add 1 to the least significant pair of bits, the result will be 2's complement. So what you have to do? So after getting the 1's complemented data by using NOT gates, 1 can be added to the sum through the input carry. So when you want to add, instead of putting the carry 0, input carry 0, if you put the input carry as 1, then it will be equal to adding 1 to the 1's complemented data. So you can see that then how to obtain the circuit. So we have obtained, so here for subtraction we require, we will be performing the subtraction a minus b actually by adding the 2's complement of b to a. So here we have seen how to get 2's complement of the data b, that is by using NOT gates. We'll be able to get 1's complement by adding the input carry as 1. We'll be getting the 2's complement of b, and now we can add the 2's complement of b to a, and you know that this addition of the data is possible by using a parallel adder, that we know already, right? So since in the previous classes we have seen how to add the two data each containing 4 bit by using parallel adder. So now, even though we are performing subtraction now, b minus b, but it is actually addition of the 2's complement of b to a. So from circuit point of view, we'll be performing only addition, but here not addition of a plus b, but it is addition of a plus 2's complement of b. So we already obtained 2's complement of b by some means, that is by using inverters. Now the same addition can be performed by using the parallel adder circuit that we have discussed previously. So instead of, so here we have added a with b, but instead of b1, what we will be doing, so the circuit for subtracting a minus b consists now of parallel adder with inverters placed between each data input b and the corresponding input of the full adder. So instead of giving the b data bits directly, what we'll do, we'll insert an inverter, a NOT gate, one for each bit of the data b. So that is for b1, b2, b3 and b4. For each of this, Before directly applying these bits to the full adder, we'll be adding a NOT gate in between. So the output of NOT gate will be, if it is B1, then the output of NOT gate will be B1 bar or B1 complement. So in that way, we'll be using 4 NOT gates, and each of NOT gate will be giving the complement of its input as output, and the output of each NOT gate will be applied as the second data bit for the full adder. As we know that full adder performs the addition of 3 bits, that is the 2 bits, the 2 data bits which are applied at its inputs, not these 2 bits which are applied at its input. So here the applied input, for example, for the first full adder will be A1 and B1 complement. Since here we have not shown the NOT gates, but for subtraction we assume that there will be a NOT gate before the B1 is applied to the full adder. So there will be a NOT gate here. So the output of NOT gate will be B1 complement, and that B1 complement will be given as input, the second input for this full adder. One of the input is A1 directly. So here for the first full adder, the inputs will be A1 B1 complement, and for the second A2 B2 complement, and for third one it is the inputs are A3 and B3 bar, and for fourth one it is A4 and B4 bar. So this is the case when we introduce 4 NOT gates for the B1 B data inputs, data bits, before they are applied to directly to full adders. And in the same time, so all these NOT gates will output 1's complement of the data bits, but to get 2's complement we require to add 1 to that 1's complemented data. So how to add 1 to that means, so there is an input carry for this addition. Normally we'll keep this input carry as 0, that is C1 as 0. So in order to add 1 to this 1's complemented data, B data, we make this C1 1. So we'll make the input carry C1 must be equal to 1 when we want to perform subtraction. So if you make the input carry equal to 1, then this addition of 1 makes this 1's complemented B data to 2's complement of B. So then this addition by using 4-bit parallel ladder effectively becomes A plus 2's complement of B, that is A minus B. So mind that the operation thus performed becomes A plus the 1's complement of B plus 1. So that is A plus 1's complement of B plus 1. You can see that this is equal to A plus the 2's complement of B, that is effectively equals A minus B, that is subtraction of B from A. So now let's look at how to perform. So here we have shown that so this is parallel ladder circuit, And here what we have explained is how to modify the same circuit to perform subtraction a minus b. So we have explained the concept, that is how to convert the subtraction operation a minus b into the addition operation, but not it is a plus b, but it is a plus 2's complement of b. And we have shown the required hardware, that is NOT gates, that are to be included for the b inputs. But by introducing the NOT gates in that way, we would be able to perform only the subtraction operation of the 4-bit data. So, but what we have, what we are to discuss is not the separate circuits for both adder and subtractor, but we want to discuss about the circuit which can perform the same circuit which can perform both addition and subtraction of the data. So only one circuit must be there which at any time performs either subtraction or addition of the 4-bit data provided A and B. So what are the modifications for the circuit by which we can perform the two operations with a single circuit, that we are going to see now. So this is 2's complement, parallel adder and subtractor. You can see that the addition and subtraction operation can be combined to one circuit with one common binary adder. And how this is done is by including XOR gates with full adder. So to make the subtractor circuit, what we did, we included NOT gates with B inputs. But to make that one circuit work for both adder and subtractor circuits, what we are doing is we are including not gate, not logic gates, but we are including the exclusive gates. We can show the actual combination logic which performs both addition and subtraction by controlling, by having one control bit. And here you can see that except this XOR gates and except this one bit called control bit called M, the combination circuit is same as the parallel adder circuit. So to perform the NOT operation, before slide we said that we have to introduce NOT gates for the B inputs, but here um, we have included the XOR gates for the B inputs before the B input goes as input to the full adder. So why this? Because so X adder, because we'll see the property of XOR gate now. You can see that this is XOR gate. This is your XOR gate, Assume that one of the input is A. Let us assume that the input is A, and assume that the other input is 0. Instead of this, assume that change we assume that one of the input is B, and here the other input is 0. So what will be the output of XOR gate? How to find the output of XOR gate when one of the input is B and the other input is 0? You can see that how to find out actually. So the output we assume that is Y, and you know that Y equals A bar B plus A B bar. So here you assume that A is equal to 0. So B is there as it is. Don't know whether B is 1 or 0, but in general we assume this bit as B itself, and for the time being we assume that A is equal to 0. So substitute, so to get what is the output of XOR gate in this case, we substitute 0 for with the A in the Boolean expression for the output of XOR gate. So if we substitute this, this is A bar B, that is 0 bar, that becomes 1. So it is 1 dot B and plus this is A dot B bar, that is 0 dot B dot B bar. So if you can simplify this, you see that 1 dot something is something, that is it is equal to B itself, and what is this plus 0 dot B is 0, and if this that 0 is added to this, it will be B itself. So here in this case the Y equals B, Y equals B. So that means when if you give two inputs for the XOR gate, and when one of the input is 0, the output is same as the first input. Very important, you can see that for an XOR gate, if you give two inputs, the first input and second input, so first input is B, second input is 0. So that means when the second input is 0, the output of XOR gate will be same as the first input that we have shown here, that is Y equal to B. And similarly, we say what happens when the second input is 1. So again substitute the same expression, 1 for the A. So here we'll be saying that this one is equal to, so this is another thing. So the expression becomes, for a we will be substituting 1 because the second input is 1. So this becomes a bar b. So that becomes, it is 0 dot b plus, and it is a dot b bar. A is 1. So 1 dot b bar. So you can see that this one equals 0 dot b is 0 plus 1 dot b bar is b bar itself, and that b bar plus 0 is b bar itself. So here you can see that it is equal to y equal to, now it is b bar. So one interesting thing that you notice here, it is that for an XOR gate, when the second input is 1, the output equals the complement of the first input. For an XOR gate, when the second input is equal to 1, the output of XOR gate equals the complement of first input. So overall you can see that when the second input is 0 for the XOR gate, the output will be same as the first input. This is the case. When second input is 1, the output of XOR gate equals complement of first input, that is y equals v bar. Or otherwise we can say that for an XOR gate, if you want to complement a bit, if you want to get a complement of a bit by using XOR gate, you have to apply that bit to one of the input of XOR gate, and the other input of XOR gate must be 1. Then the output equals the complement of the bit. So this is how we obtain the complement of any bit by using XOR gate. So if you want the complement of the bit by using XOR gate, you apply that bit as at one of the input of XOR gate, at the other input you apply bit 1. The output of XOR gate will be the complement of the bit applied. Similarly, if you do not want to complement the bit, that is, for bit b you want output of XOR gate output also the same as the bit, what you have to do, you apply the bit to one of the input of XOR gate, and at the second input of the XOR gate you apply 0. When you apply this way, the output of XOR gate will be same as the applied bit. So y equals b. So this will be using, this concept will be used so either to complement the bits or not. So the complementing bits, so you apply bit b at one of the input always, but the second input of the XOR gate you either apply 0 or 1. So when you apply 0, you want to get the output same as the applied bit. When you apply the bit 1, when you want to get the output of XOR gate, the complement of the applied input bit. So this concept will be used to combine both addition and subtraction operations into one circuit. So this is why the XOR gate is used here. So the B bits are applied, B bit is applied to one of the input of XOR gate, and the second input of XOR gate is placed in the control of the second bit, that is whether it is 0 or 1. is placed in the hands of the user. That means if he wants to perform subtraction, he has to apply a bit 1 in the second input of XOR gate. If you want to perform the addition, he has to apply a bit 0, the second input of XOR gate. And this control will be calling it as the bit M. And here you can see that the bit M, the control of M bit, is connected to the second inputs of all the 4 XOR gates. Connected to 4 inputs of the XOR gate. So whenever the bit M equals 0, what it means? The second inputs of all the XOR gates are 0. And when the second inputs are 0, the output of XOR gate will be same as the first input. That is, for this XOR gate, the output is B1. For this it is B2. For this it is B3. For this it is B4. That means what goes, and you can see that the M, when it is 0, it is also connected to the input carry of the parallel adder, which is C1. That is, C1 is also equal to 0. So now what the full adder performs, actually receives each position. This full adder receives A1 B1, this receives A2 B2, and this full adder receives A3 and B3, and this full adder receives A4 and B4. So that means this full adder now performs the addition of A1 plus B1 along with its input carry C1, which is also 0 as M is 0. Right, so now the addition is performed and someone S1 is produced and C2 is produced and given as the third bit for the second full adder, which adds C2 along with A2 and B2. So this performs the normal addition of 4-bit data when M is equal to 0. That you can see that. So the mode input, this is called M is called mode input, which controls the operation to be performed. And when M is equal to 0, the circuit is an adder, 4-bit parallel adder. Why? Because that B XORed with 0 will be B itself, as we have seen previously. So that means the full adder receives now the values of B, and also the input carry is 0, and the circuit performs A plus B, and the data bits of A are added with the data bits of B, so it performs the normal addition. Now in the second case, when the user makes this M equals 1, you can see that when M equals 1, you can see that all these M's are connected as second inputs of all the XOR gates. So M is 1 for the second inputs of each XOR gate is equal to 1, and the first input is the bits B bits, that is B1 here, B2, B3 and B4. So what happens for this XOR gate, we'll see first. So one of the input is B1, the other input is 1. So that means when one of the input is 1, output of XOR gate will be the complement of its input. So here the output of XOR gate will be B1 complement or B1 bar, and here the complement will be B2 bar, and here the inputs are B3 and 1, so the output is B3 bar, and here it is B4 bar. So we can see that the inputs received by the full adder for this, it is A1, not B1, so it receives B1 bar here. So A1 B1 bar, and what is the third input it receives is the input carry. So since this m is 1 and m is connected to the input carry, C1 is also equal to 1. So the first full adder receives the bits A1, B1 bar and the input carry 1. So B1 bar plus 1 makes the data bit, the data B, to a 2's complemented data. So now what is added is A1 plus B1 bar plus 1. So this will is effectively equal to A plus the 2's complement of B, and here it produces sum 1 and the carry goes to next full adder, and here what it adds, it adds the bits, it receives the second full adder receives the bits A2, B2 bar and C2, produces the sum S2 and the carry C3, and what this full adder receives, it receives A3, B3 bar, so it adds A3, B3 bar and C3, produces S3 as sum, C4 as carry, and this last full adder receives the bits A4, B4 bar and C4, produces the sum S4 and the carry C5. So now it effectively performs. So what it is adding, it is every full adder receiving A1 bit directly, but B1 bits complemented. It is B1 bar, B2 bar, B3 bar and 4 bar, and it is also taking the input carry as 1. So this makes it as the addition of A plus 2's complement of B, so which is equivalent operation of A minus B. And you can see that when M equal to 1, the circuit is a subtractor. We have B XOR 1 equal to B bar in each case, and the full adder receives the 1's complement of B. So each full adder receives the 1's complement of the corresponding data bit, and the input carry is 1, and you can see that the circuit performs now the operation of A plus the 2's complement of B. It is equivalent to the operation A minus B. So the same circuit is can be used as either 4-bit parallel adder when you make m equals 0, and it can also be used as 4-bit parallel subtractor when this m bit control bit is made equal to 1. So this completes the explanation of the 2's complement parallel adder subtractor circuit. So to check whether to check the working of this parallel adder circuit, we can apply the data bits here. We can apply the data bits and check the working of the 2's complement adder and subtractor perfectly. So that we'll do as a last step in this explanation. So here the A bits, A data is taken as 1 0 1 0 0 and 1. So this is the data 1 0 0 1 is the data of A. So A data is 1 0 0 1 and B data is 0 1 1 0. So 1 0 0 1 minus 0 1 1 0, that is the subtraction that we want to perform. So 1 0 0 1 0 1 1 0. So this is the operation that we want to perform, and you can see that how this is performed. How this is performed, we may actually writing the A data as this, and we are obtaining the ones complement of the B, that is 1 0 0 1, and for this ones complement we will be adding 1, so that becomes the 2's complement, and we will be adding all the 3. This is 1 plus 1 plus 1 is 1, 1 along with the carry of 1. 0 plus 1, 0 plus 1 is 1, and here it is 0 plus 0 is 0, and here 1 plus 1 is 0, the carry of 1. So here you can see that this is how the circuit will add. We will be doing this, and result is 0 0 1 1 sum with a carry of 1. So we look at how this is done by the circuit called 4-bit adder add subtractor circuit. So here the bits are applied, and here this is a subtraction operation, so m bit is 1, so the second input of all the XOR gates will be 1, and the carry input is also equal to 1. Now you can see that, so this XOR gate, one of the input is B1, that is it is 0, and the second input is 1, so it complements the output of XOR gate will be the complement of B input. So B input is 0, so the output of XOR gate is 1. Similarly, output of this XOR gate will be a complement of B2, that is it is 0. So B2 is 1, so the output of XOR gate is 0, and the output of this XOR gate is the complement of B3, which is 1. Complement of B3 is 1, so output of XOR gate is 0. And for this you see the output of this XOR gate is the complement of B4, and since B4 is 0, the output of this XOR gate is 1. And now you observe the inputs received by this first full adder. It is 1 for A1 and 1 for the complement of B1. So 1 plus 1, C1 will be 1. So this is a M1 is 1, so C1 will be 1. So 1 plus 1 plus 1, sum is 1. Sum is 1. And you can see that sum is 1 and carry is 1. So already indicated. And for this second full adder, the inputs are 0 for A2, 0 for the second input, which is a complement of B2. So 0 plus 0 plus 1, the sum is 1, the carry is 0. And for the third full adder, the inputs bits are for this full adder 0 for A3, 0 for the complement of B3. So 0 plus 0 plus 0, sum is 0 and the carry is 0. And for the last full adder, 1 for A4 and 1 for the complement of B4. So 1 plus 1 plus 0, the sum is 0 and the carry is 1. You can see that the result is 0 0 1 0 0 1 1. So as we did in the previous hand calculation, the subtractor is producing the same difference, that is the difference is 0 0 1 1, with a carry with a borrow of 1, and I can say the result is 10011. So this makes the working of explanation of the working of the parallel adder cum subtractor complete. Thank you.